All right, so last time, if you recall, last time we talked about the big data, and by the end, since we were running out of time, I covered a little bit why there's a fundamental need for big data. In terms of modeling, machine learning, everything. Why big data is so important. So there's a phenomenon called the curse of dimensionality. It's very important. That will basically set the foundation for you to understand why machine learning models. And it also explains why the first step of a lot of machine learning model is to reduce the dimensionality, which we call feature extraction. So let me just try it here. Feature extraction. I don't know how to make this pen thinner. Anyway, I tried. See, like this? Nope. Okay, anyway. All right. So I'm going to give an example, quick example showing that why at the beginning adding more independent variables or X can make a model better. So let's say we want to predict a building subsidence. The building subsidence shows, after you build a building, because of the foundation, because of the soil behavior, the building will basically go down, right? And over the year, it will just keep going down, right? So let's say at the very beginning, we have this 1x, which is the years. So now, in order to build this relationship, we model something, right? We collect data from the field, and this is x1, which is what? Years. And this is the subsidence in meter, for example. So let's say you collect some data showing, oh, this is year 1, this is subsidence, and this is year 2, year 3, and you start to have all data points. So this part is data collection, correct? And then what's your next step? You want to build a formula. So basically fit a line. And you find out y equals fx, 1. That makes sense, right? Anybody? Okay. So now you start to see a lot of variance, right? The noise from the actual data. So there's no perfect model to basically go, a perfect model, a perfect line to go through all the points, which means we still have something not captured. For example, can any of you name me another X that can help us improve the model? Anybody? Did I lose you guys?
Yeah.
No? Can any of you name another X showing to improve? How about this? Let me show this. Okay, let's say the number of stories of the building. That makes sense, right? So the taller the building is, the heavier it is, so the subsidence could be severe. Makes sense, right?
Yeah.
Okay, all right, thank you. So in this way, think about this is actually we are moving from a 2-dimensional space to a 3rd-dimensional space. Like I'm going to add another X, which is the number of stories. And then we still have the same data points, but all these data points will basically, these data points are the projection of the 3D space data points to this 2D. But now let me reproduce them back. Let me send them back. Then what do we have probably would look like this. Let me just erase all the data and also this line. So then after we collect all the data, adding that new function, probably I have this new way of all the data points. That's in a 3D space, not 2D anymore. And in this way, if I build a new model, y equals f x1, x2. That is actually what? Actually a plane, not a line anymore, but a 2D plane. Make sense? And then the model quality is actually the distance from the point to that plane. But of course, there's still noise, but I know the total noise, let me just use this one, total noise, L arrow, should be smaller than the original noise of its 2D. That makes sense, right? Because we add this new additional information. That's correct, right, guys? All right.
Yes.
So far, so good. All right, thank you. All right, so can we also add more? Yes, let's say type of soil. Of course, I cannot visualize in this graph. That will be a 4D graph, but we can know mathematically the arrow will become even, the noise for 4D will become even smaller. All right, so far the story looks great, which means let me just keep add more X so I can improve my, right? So this is a predicted Y, this is actual Y, so I can improve it to make it smaller. All right, so that's why there's an intention for engineers to keep adding variables. So think about not just for engineers. If you are a stock broker and you are trying to invest in some stock, you want to predict the price of it, you could consider the GDP of the country, the past profit of that stock, or you could just check the recent news, the unemployment rate, or maybe the Bell party election, right? So there are so many things you could consider, which means we keep adding X to make the model better. That is true from this perspective, but it doesn't apply when one thing happens, when you are adding too many X and when you don't have enough data. So let me just go back to this example and see what happened. So when we add more X here, we forgot one thing is the representativeness of my samples. Of course, I cannot collect the years and the number of stories and the types of soils for all the buildings around the world. I'm always doing, so this is actually the population. That's everything, right? But what I can do is just a small set of that. That's called a sample. A good sampling means I sample something here, from here, from here. So that's actually all the sample I have. That is actually showing my sample is representative. So that's very important. All right. So let's see, in order to find the good year to the subsidence relationship, I need at least a 20% coverage of all the population. So which means my sample size is about, that's not that much. Let me just, so which means my sample size should be, let's say here, 20% of the population. Let's say that's the rule, okay? Then it looks like this, right? So let me use different color, like right. Maybe something here. Let's say all the red points, that's around 20%, okay? Now let's say, let me erase here and use this. Let's say I add a second, that's x1, and let me add a second x2, and this is the number of stories. I still need 20% of coverage. If I basically replot this data, you know, here, let me see, this one comes here, this one comes here, this one comes here, 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 here. Okay, so basically I'm going to, oh, I'm sorry. I remove original one, and here I basically project all the original samples to this space. Is that 20% anymore? Can anybody tell me? Hello?
Can you repeat the question, Professor?
Yeah, so let's say in order to have a 20% of X1 plus X2 coverage, so in this space, I need 20% coverage of data. Do I still just sample 20% here and sample 20% here to get it? No, right?
No, that might reduce.
Yes, so because the average coverage is actually 0.2, the square of that, right? So it's only what?
4%.
Exactly. So if you have sample here 20%, sample 20%, but the overall coverage for that is actually lower than 20%. So what is the coverage I should sample from X1 and X2? So can anybody tell me the square root of 0.2? Anybody?
Like 4 point something.
Okay,
I mean 40 point.
Okay, so that's what? That's actually X. Not. Let me use a different number. A. Okay, that should be 44.7%. What does that mean? That means that in order to cover 20% of X1 and X2 all the data, I need to sample about 45% data on X1 and 45% data on X2. That makes sense, right? So let's say originally I have this 1 year, 2 year, 3 year, buildings, but now I add another, variable, which is let's say 10-story, 20-story, and 30-story. Do I have other combinations? Definitely no, because I could have 1 year plus 20-story, 3 year plus 10-story. I could have 2 year plus 10-story, blah blah. So basically, when you add a new dimension, you actually need exponentially more sample ability for each X, right? So let's say if I want to consider all the 3 variables in this example, let me do this. Let's say I want to have a model with all the 3 X, X1, X2, X3, okay? And also, again, I want this sample to be about 20% of the space formed by X1, X2, and X3. Then it's to, let's say, I sample A from here, A from here, A from here. So it's actually A square, A cube equals to 0.2. Then what is A?
1027.
What's that?
1027, I guess.
7, 8, right? Did you guys notice the problem now? I need a representative. I need my data to be representative to generate a really good y equals f, x1, x2, x3 model. And I know the bottom line for me is 20% of all data. But when you add just 3 variables, the actual sampling for both x1, x2, and x3 just dramatically increased to 78%. That's pretty much everything. Now imagine if you have 7, what would happen? That's almost 99%, which is impossible. Make sense? So that's actually the first feature of Curse of Dimensionality. Whenever you are adding, so let me just totally remove the entire page. Whenever you're adding when adding mod x, the sample size will need to increase exponentially. So that's the first feature of that. Okay, but it's not all of that. You say, you know what, professor, we have the sensing network, we have the Internet of Things. It's possible for me to sample 90% X1, 90% X2. Is that okay? The answer is still no, because there's some weird behavior of Curse of Dimensionality. That behavior is none of your samples would be representative. What I mean? Let's do this. I have this, square, and the length is the side is 1, and I also have this, incredible circle. And so what can be considered as representative data in A or in one of the corners? What data should be considered as representative? Let's say that if this is LX1, if this is LX2, this is a space. In A or B, representative data? Anybody? Should be the data from A, right? Make sense? You guys are quiet. I cannot hear you guys. Can anybody?
Yeah, I mean,
Okay, all right. So let's do a quick calculation. What is the size of the square?
1.
Is 1. Okay, so I say that let's say the square is represent our population. So that's all data. Let me see. All data size equals 1. So what is the size of the circle?
Pi divided by 4.
Yeah, so this
the radius is,
yeah, the radius is pi r square. So what's that? Can anybody tell me? I'm doing that too. Around what?
0.78.
So around 0.78. So then what can be considered as outliers, which means, from these areas, from this area, should be what? 1 minus 0.78 should be what?
0.22.
22%. So which means if you just randomly sample from this space, there's a 22% of chance you sampled something that are not representative, representing extreme situations. Make sense? Okay, now let's say this is a 3D cube. And the side is still 1. And we have this sphere inside. So what is the size of the all data? All data size should be what? Should still be 1, right? It's the volume of the cube. So that's 1 times 1 times 1. That's still 1, right? Make sense?
Yes, yeah.
Then what is the size of the circle, or the representative space size, which is the volume of this 3D sphere? So that is what? I cannot recall the function, the formula for that. Can anybody tell me?
Mm.
Anybody?
It is
You're
4
asking
by
for the
3
volume
pi r
of the
cube.
sphere?
4 by 3 pi r cube.
Actually, I know the answers. Let me just.
0.52.
Okay, so 0.52. Then what are the outliers? The chance that you have sample outliers is what?
48%.
See, that also increased a lot. And more than that, guys, let's check this diagonal. So for this 1, 1, what's the length of diagonal? 1.4, around 1.4 here, right? Then what is the diagonal here? From one corner to another corner? Actually, that's a 1 plus 1 plus 1, right? And that's actually, let me tell you this, it's actually 1.73. What does that mean? So this corner and this corner are moving away from each other when I add a dimension. So when I add this new dimension, the corners are becoming further away from each other. More than that, the number of corners also changes. So for a 2-dimensional space, the number of corners are what? 4. So actually that's what? 2, the square, right? And for a 3-dimensional space, the number of corners equals to 8. That's a 2 to the power of 3. Okay, so now we cannot see the higher dimensional space, but we can definitely visualize how it happens. So let's say for a 7-dimensional space, what would happen? Which means, when I add a model, like predicting the subsidence of my building, and I added 7x because I believe I'm so smart. I know a lot of things, so I basically add 7x in my model. let's do a quick calculation here. Number of corners equals to what? To the power of 7. That's actually 128 corners. Then the diagonal distance is what? So let me show you the number. It's actually 2.65. And the size is actually the volume of the encrypt hypersphere is what? Let me tell you this. It's actually about 0.963. So the outer layers actually equals to what? The outer layers in terms of the divided by the entire data actually equals to, oh, sorry, here, wrong. This is 0.0369. And this is actually around 96.3%, which means you can try to sample a lot of data from the space, but likely there's a 96.3% chance that what you sampled are actually extreme values. So now let me switch to my PowerPoint, and this is how I visualize that. So I'm going here, share. You guys can see my screen now. This is actually how we visualize, 7-dimensional data space. It's actually a weird space with 128 corners, but about 97% of the space are actually the corners, and the center place is only about 3% of all the data. Think about what that means to you guys. It's not just that you have to increase your sample size. It also means whatever you do, whatever you try to get the most quality, the high quality data, the most representative data, I can tell you 97% chance your data is actually extreme cases, not normal cases. That's actually something very difficult to imagine, but it's actually happening whenever you're increasing your dimensionality. That makes sense? And that's also why in statistics, when you are increasing your dimensionality to, let's say, more than 7, it will be extremely difficult to come up with a possibility density function, PDF. The probability density function is actually a formula for us to describe how data spread in the space, right? And that is based on the data. It's based on I collect a lot of data, and then I basically feed a formula to describe the spread feature of the data. But when it approaches 7 dimensions, it is so important for us to feed a formula to describe how data is spreading, because data is basically spreading to the extreme corners. There's no knowledge at all. And because of that, just recent, this paper also discovered a very interesting phenomenon. If you can read this formula, maximum distance, basically you just randomly pick 2 points from a high dimensional space, and you calculate all the distance, and you find out the maximum distance, you find out the minimum distance, the furthest pair and the nearest pair, they are pretty much the same. What does that mean, guys? It means all the data, the distribution information will be lost. There's no cluster of data, like, okay, so some data are more clustered in this area, some data are more spread further away in that area, so this is probably a normal distribution, and the center shows a higher density of data. No, when you are beyond 12 dimensions, this rule start to appear, and you randomly pick one point and randomly pick another point, and just randomly pick the third point, randomly pick the fifth point. You calculate the pairwise distance. They're almost the same. They're almost the same. So there's no concept of near or far. Statistically view disappear in such a high dimensional space. Okay, so this is actually what we call the curse of dimensionality. It's very difficult to understand, but we can definitely see how that is affecting this. You know, like in machine learning, I mentioned that people tend to add more dimensions to describe the model. And we also have seen this from the weather prediction model, right? From the first model in 1922 with only 10x to the recent model, you know, with more than 2 million parameters. That's more than 2 million x. In machine learning, same thing, you know, want to predict if this is a cat or dog. I could use, I say, the ratio between the head and the body. I could use the color. I could use the position of the ear. So that's all features, all x. Y equals fx, or y equals some features. So we have already discovered that when you increase dimensionality, your model performance will always improve, but after a certain point, the performance will decrease very fast. That is because of curse dimensionality. When you are increasing that, you are losing the ability to sample enough, like 20% representative data from your data space, but also no matter how hard you try, you know, you just cannot find quality data at all. Okay, so if we put them in this way, you know, here are 2 ways we can treat our model performance. You know, one way is to add more variables. This is actually the fundamental pursuit of knowledge, like, oh, we want to add more knowledge to our model, or to increase the sample size. And this one we have this, and Y is the model performance. This one we have this 3D landscape of that. It shows that giving the existing sampling ability, like a data sensing ability with the sensors to track your concrete performance, everything, giving the existing that, yes, if you add more variables into your function, the performance will increase, but at a certain point, it will start to decrease. And the only cue is to increase the sampling of your model. But when we hit this wall, which we call the Aptismatic Wall, it's the inability of human beings to sample more data. It's just impossible for us to get more data. And it will ultimately hit this wall, and then we will definitely see the decrease of your model performance. So how to push this wall further? That's actually big data. So that's why traditionally, you know, something we didn't believe them to be valuable data, like a human conversation, the natural language. About 30, 40 years ago, we didn't think that's data because they are not structured. But now we actually try to make good use of that. Like Facebook, Twitter, you know, we have the algorithms to analyze the meaning of that, because there's a fundamental need for us to push this wall further. Otherwise, we're going to face this huge decrease of a lot of models we are developing. Make sense? You guys are quiet, but I really want to stop here for a moment and answer your questions, if any. Any question, guys? No? No question, no comment? So did you guys understand the curse of dimensionality thing now?
Yes.
I cannot see your face. I just heard it, yes. All right, and there's another thing, okay? So even though one day, let's assume that one day we push this wall really far away, that shows the magnitude of the problem. So let's say we do have the ability, humans do have the ability to cover the scale of the problem. We can sample a lot of things, but still our universe plays the trick with us, which is the accuracy of your measure. So I'm going to show you this Excel spreadsheet. Oh, I cannot do that. Let me just stop sharing this one, but share my screen one. Okay, you guys can see this my Excel. So this one shows you know, this is the iteration function, you know, which means the second value depends on the first value, and this is the function. Very simple. It's this number. So now the value of this number is 3.8 times this number times 1 plus this number. So this 0.18 is actually equals to 3.8 times 0.05 blah, 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 0, 1 times 0.05 minus 1. So that's actually how we got this second number. And third number, same thing, 3.8 times this number times this number minus 1 minus this number. So we just got this one, all right? So this one is called butterfly effect. So you guys have watched the movie Butterfly, right? It shows that if you just change something really, really small at the very beginning, it can totally change the entire trend of your development of your curve. So let me just do a quick trick here. So the first value here is 0.05. Okay, so I'm just going to change the first value to 0.05000002 and observe what happens to this curve. You guys see the after about 40 runs, the curve totally changed. So let me just do that again. Let me change it back to 0.00000001. See what that changes? Dramatic change. What does that mean? A lot of engineering systems are iterative systems. Like if you're calculating the force of a bridge, your result will become the input of a next calculation, and etc. So it will keep going. And we cannot measure that force or dimension or whatever engineering parameters to the most perfect level. Maybe at the atom level, right? It's impossible. Yes, we could push the accuracy, but the precision, but no, we just cannot push it to the ultimate perfect precision. But because of this sensitivity to the initial state of the system, or what we call the butterfly effects, even you just change it slightly, the entire system behavior will change dramatically. That means what? If you consider everything, we do have the fundamental desire for precise knowledge or better knowledge, so we want to add more dimensions. But because when we add more dimensions, the need for sample will increase exponentially. And even you could have all the bigger samples, but because the curse dimensionality, you will see you start to lose the representativeness of your data. That all the data sampled from you would be considered as all the layers. So there's no way for us to feed this distribution function or to understand how the data spread. And also, even though you could cure the curse of dimensionality and people are developing methods for them, still there's no way for you to achieve the ultimate perfect precision in your measure. And because of that, we do find a common solution, which is big data. We do need to rely on the big data to get more data and to cure all the problems. Okay, so I'm going to stop here. It's already over 7:05, but I'm just going to stop here for maybe another minute. Any question, any comment, guys, about this curse of dimensionality? You guys are tired, right? So I can show you quickly. Just I promise this is the one last note here. Oh my goodness, here it is. If you search the key, sorry. If you search, the keyword curse of dimensionality and the machine learning, you will see actually the departure point of a lot of machine learning is actually the curse of dimensionality. The machine learning is actually trying to reduce the dimensionality of the space, so to solve all the problems. Okay, we will talk about that later. All right, guys, thank you, and see you guys next week. If you have a question, comments, let me know. All right. See you.
Thank you, Professor.
Bye-bye.
Thank you. Bye, Cut.